Good morning, Fiona. How are you?
I'm good, thank you.
Brilliant. So I just gave you guys a quick intro into yourselves. So if you could share your screen and I will hand over to you.
Okay. That should have worked now. Okay.
Great.
Yeah. Hello, everyone, and welcome to my presentation about additive manufacturing from the research and industry perspective, and hopefully to answer the question of how to fit the smaller into the bigger picture. So just to give a little bit of an introduction to myself, I'm just going to give you a brief intro. So I started my engineering journey by studying production engineering. And while I touched on a lot of different engineering disciplines, like manufacturing engineering, for example, I felt particularly drawn to materials engineering, material science, and specialized in metals. I then took that further and did a PhD at the University of Birmingham in the UK. And I started to specialize in high temperature, high performance materials because I just found the application so interesting. But up until that point, I didn't really have anything to do with additive manufacturing. In fact, I was working on forged materials, so quite a way removed. But in my first job after my PhD, which I did as development engineer at Material Solutions, which now belongs to Siemens Energy, I first discovered the wonders of additive manufacturing because I started working on SLM or LPBF and made functional components for aerospace and space applications. And I found this technology and the challenges that this technology brings with it so interesting that I moved on into research because I wanted to learn more and I wanted to know more. And so I'm now investigating additive manufacturing, the powder-based additive manufacturing techniques, and really trying to link the process to the material structure to the performance of the materials. And so this is how I've come into additive manufacturing, and really how I learned that you have to speak both languages in a way, of industry and of research, right? And that's what I want to talk to you about today. So of course, additive manufacturing, especially in terms of a metallic additive manufacturing, is an incredibly fast-moving technology, and that brings a lot of challenges. And because there's so much happening, for simplicity's sake, I'm going to focus on SLM or LPBF examples in this presentation, but what I'm showing is hopefully applicable to really all the different additive manufacturing techniques. So from a research perspective, when we look at this fast-moving technology, we ask, what is possible with AM, right? We think of all these different things that we could do with this technology. And of course, as researchers, we risk sometimes getting lost in the detail because there are always more questions to ask, right? Always more questions to answer, and a good piece of research and asks more questions than it answers usually. So it's a never-ending process, and it's a lot of rabbit holes to get lost in. So from the industry perspective, when we have this fast-moving technology, then we're asking, does AM make sense for part X, right? And that's really the interesting application. But of course, if we don't know enough about the technology, then we're maybe at risk to select a part that's way too complex or maybe way too simple. So in either way, the business case is suddenly in danger, right? That's something we don't want. We want to push the technology, but we don't want to shoot outside of the field. And I thought to illustrate the push and pull between research in industry, I would bring two examples. So the first example is going to be something where we know where we want to go, right? We know about the application, we know the part that we want to manufacture, and now we have to fill in the bigger picture with all the little bits of research to be able to get there. And the first example that I'm bringing is the turbine blade. It's what everybody in metal additive manufacturing wants to manufacture, because it is such an intricate and very, if I speak for myself, very cool application. And if we go to the most advanced gas turbines, they're the ones that are flying. So they're attached to the airplanes. They're pushing our airplanes forward and enabling all our trade and travel as well. So just to give you a quick recap, in case you don't know how it works, very simply, we pull in air at the front through the fan, and then we compress the air through several compressor stages. Then we mix it with fuel in the combustion chamber, ignite it, and then the hot air is released through the turbine, and that's really what drives the thrust, what moves the airplane forwards. And this compressing and the releasing in the turbine is happening in alternate stages. So you have a rotating stage, and then you have a stationary stage. And the turbine blade, of course, is in the turbine, right behind the combustion chamber. And so it's the hottest part of the engine. It's the most demanding area of application in terms of load, in terms of temperatures and everything. So, and on top of that, it is rotating. So it has the rotational forces working on it as well. So it really is the hardest working part in the engine, while the whole engine, of course, is working very hard. And to make these gas turbines as efficient as possible, this turbine entry temperature right after the combustor needs to be as high as possible, because the higher that temperature, the more efficient the engine. And that means that this temperature, of course, gets pushed and pushed. And in fact, it gets pushed beyond the material capabilities, so above the melting temperature of the materials. And you might ask, how is this possible, right? And that's because of a lot of research. So decades and decades of research have gone into the manufacturing of turbine blades. And it's done by a casting, and it's so specialized and so well honed that a full turbine blade is cast in one single crystal. If you're interested in this more, I recommend looking this up, because it's a really cool technology. But it, of course, means that decades and decades of research have gone into this part already. And now we come with this new technology, right? Now we have additive manufacturing, and we say, we would like to try to make these parts in additive manufacturing. But we're starting quite a bit lower than what we've already done with advanced casting. So why would we bother in the first place? Well, we would because it's a very intricate piece of engineering, and it only works because of its advanced cooling and other material-specific stuff, but specifically the cooling channels are what make these parts able to operate at the temperatures that they do. And if you know additive manufacturing, or you've heard a little bit more about additive manufacturing in this conference, you will know that internal features, and especially cooling channels, are one of the topics where additive manufacturing jumps on the parts, because it's possible now. We don't have to think about how to maybe drill into the part. No, we build the part up layer by layer. And so internal features, as long as we can get the powder out in powder-based manufacturing technologies, are possible, and we don't have to think about them too much. So we have this piece of technology that is very advanced, and that seems to be quite a good case for additive manufacturing. But of course, we now know that we have to get to quite a high level in terms of knowledge, right? So we need to fill in with research. You want to manufacture the turbine blade. So what do? Well, maybe we start by looking into understanding AM materials. AM materials have a material structure that we haven't seen before, because we haven't manufactured parts like this right? This layer by layer by layer by layer. And when we do this, well, maybe we want to look into alloy development, because maybe we find that all the alloys that have been developed so far were tailored to the specific manufacturing technologies. And maybe we need something different for AM. And once we have the alloys that we want to print, well, then we need to do the whole process development, right? So that we can process them in a way that we get solid parts with the properties that we want. And when we know how we want to process them, well, then maybe we want to do some design development. Maybe we learn something along the way and we improve and improve and improve. But of course, as everybody knows, in metal AM, when you want to make functional parts, you need to account for post-processing. And maybe you need to tailor it specifically for the application. Maybe you need to look deeper into it. Maybe you can get rid of something that you cannot avoid during the process, like maybe some support structures, or maybe surface roughness that you cannot reduce any further with your printing technology, but maybe during post-processing. Then, of course, you need to evaluate the material in the first place. And that's looking at the microstructure, for example, or also long-term properties, because you need to gather all this knowledge. You need to piece together your knowledge that you need to be able to print turbine blades. And then once you have all this, maybe you can take a step back again and then look at how can you use this technology to maybe do something that you haven't done before. Maybe you want to tailor the microstructure, something that you didn't have time for before because you needed to build all this knowledge up first. And now you can go into the benefits and really optimize the microstructure specifically for your application. And just to bring you some examples, these are really some of the aspects that people are looking into. So, for example, looking into the AM materials and trying to understand them. And this is where research has the unique opportunities that industry doesn't have. So in research, in this piece of research, for example, the researchers were able to investigate 6 different alloy compositions, right? Of course, it takes a lot of time, but having 6 different alloy compositions where you switch and change individual elements with different amounts, just to look what effect they have on your material, is the time for or the capabilities for in industry, right? It's uniquely a benefit of research. And then not only did they investigate 6 different alloy compositions, no, they went into depth, right? They looked with optical microscopes. Okay, this you can easily do in industry as well. And then did some SEM as well. This is a little bit higher resolution, and you can sometimes get that in industry as well. But these researchers went so far as to look into the atoms and where the atoms are located to really identify where are the different elements inside our material and why, and what do they do, and what effect do they have on the material. That's a very basic understanding that industry doesn't want to look into. Industry wants to know, I can use this material, right? It's a huge benefit of the research getting involved, because it can look into in depth. Another example would be researchers looking into process development. And here is another example of how advantageous research can be, because these researchers had a machine and just like that, tinkered with the hardware. So they adjusted the laser beam shapes, for example, and just, for want of better expression, played around, right? They just had a look and just tried to figure out, well, if I change this, what effect does it have? And maybe they got to a material structure that was even better in terms of mechanical performance than what you have when you use the absolute standard settings. And of course, this is also something you don't have time for in industry. In industry, you select the machines and you print your parts. You don't want to change anything, because then you don't know how reliable it is over time. This has to be done in research. Then the last example would be microstructure tailoring, where a group of researchers looked into 9 different scanning strategies, right? Or they reported 9 different scanning strategies. They probably looked into a few more, and then went into in-depth material analysis and evaluation and down selected a few, and then printed a demonstrator part and tried to see, well, if we now go beyond printing cubes, which is something we do a lot in research, but we now go into the complex geometries of a turbine blade, do we still see the same effects? And can we tailor the microstructure? And can we get the benefits into the material structure? Right. So it's very interesting to look in depth, but you have to connect it to the application at some point, because otherwise you won't really get there. So this is example number 1, where we know where we want to go, which is our turbine blade, and we know for a fact that we need to generate a heck of a lot of knowledge before we get there. But that's not the only way of how we can do things. So I brought a second example, and this is an example from my time working in industry, working at Siemens Energy. So a real life example where we connected what we already knew about the technology, because of course we're not starting at 0 every single time whenever we want to start printing a new component. We know some things already, but we need to connect that knowledge with a part. And again, I mean, working for Siemens Energy, it might not be the biggest surprise. Again, it's about gas turbines. This time, not the flying ones, this time the heavy duty gas turbines for energy generation. And the principle is the same. You compress the air and then you release it through the turbine. And again, you have the alternating stages between rotating, which on top of everything else also see the rotational forces, which is a little bit more complex to account for, and the static parts in between the static stages that are just as essential for the turbine operating. And again, the turbine right behind the burners, right behind the combustion chamber, is the hottest section of the gas turbine. So it sees the highest demand in terms of high temperature reliability of the materials. And now, well, what did we do? Well, some of these gas turbines have to operate for years and years, and that's not just 2 to 5 years. This is decades long, right? You don't want to put a heavy duty gas turbine somewhere and then have to look at it every 2 years. You want to know that it runs reliably and it can generate electricity for years and years to come. And so what that means is there are a few gas turbines around that were put into service quite a while ago. And of course, additive manufacturing was not the technology then. But maybe they've been in operation for so long that some of the casting dies are not readily available anymore. And so what happened in this example is that we had an old version of a gas turbine that is still in operation and is still generating electricity and heat. And we now wanted to try, well, if we now print these static parts, which is a guide vane instead of a rotating part, the turbine blade, can we do this with additive manufacturing? And in the very first instance, we didn't have a CAD model. We went off the casting drawings. And I don't know about you, if you work in additive manufacturing, metal additive manufacturing for industrial cases, and you've done anything like this, printing or trying to print a casting optimized design, you may sympathize with some of the frustrations that can bring with it, because it is not tailored for the additive manufacturing technology, but you have to start somewhere, right? So you start printing a demonstrator and then you analyze the demonstrator and you learn from it, and then you can maybe over time optimize it. And this is what we did. So the case was really trying to figure out whether we can generate spare parts for an old gas turbine and make it live longer, make it operate for longer because we can replace if needed. And over these few iterations in the beginning, we were able to reimagine some of the cooling systems inside and optimize them locally. And we're able to reduce the metal temperature, for example, for these parts by 250 degrees Celsius, which is quite substantial, and it's good for the operation. And then we had printed these parts, and we put 8 of these parts into a customer engine. Right. So currently, we have a few parts in a customer engine that are operating a general operation environment. So we gather data over time until we take them out in a few years. But this is not the only way of generating data, right? If you manufacture something, you go through the post-processing steps and the inspection steps. So that's all knowledge generating. So what do? Well, we do optical scanning, for example. We do metallographic analysis. We do FPI, which is fluorescent penetrant inspection, to see whether we have any surface connected defects. We do thermal imaging, for example, especially when it's a component that operates at high temperature. We do computer tomography, so we shoot X-rays at our parts and look through them. We do airflow testing. So all of this, of course, is generating data that we can then go off. So we can use this as a basis and build a database that generates more questions. So what do we do next? Well, maybe we look into improving cooling channel designs, right? Maybe we were able to do some online monitoring while we were printing, and now we have the time to analyze and interpret the data. And then maybe next we look into defect formation and what is happening during the process. Can we work against it? Can we optimize it further? Then we think about the process in general and think, well, how often can we recycle the powder and still get the parts of the same quality so that we're sure that they are reliable and we can use them in the same way as the ones printed with the earlier powder. It's something that takes time, but something that needs to be investigated also in detail. Then we can gather some long-term material degradation data, which is, of course, for high temperature applications, extremely crucial. We can do the same with the long-term mechanical properties. And we just generate knowledge over time that helps us understand how additive manufacturing materials work and how we can use it for future applications. And just to bring it together, you can summarize this with the technology readiness levels, which you will probably have heard of, and which are just a good summary of how you get from an idea to the final product. And that's, of course, through the different stages. You start with basic technology research, you do the research to prove feasibility of the concept that you've come up with. You then do the technology development, which is a lot of the stuff that we're currently doing, linking to the technology demonstration. So you print demonstrators and you show that you can connect the knowledge that you've already generated with some of the application ideas that you have. You then develop the entire system that you need to be able to manufacture reliable components. And then you test the system, you launch the application, and you have the parts in operation. If we bring this back together to the challenges of a fast-moving technology, so for one, we're investigating and figuring out what is possible with AM, and then we have our parts that are the application examples that we have. We need to connect, of course, what is possible to the actual application, but the actual application will give us a drive of trying to figure out what do we want to make possible with this technology and what should we maybe look into further. So I hope this connects research and industry in a little bit more detail for you. And really, as a big summary, it can be said from personal experience, metal AM is really more about controlling all the chaos.
Thank you so much, Fiona. We can definitely reflect that. It's so important to make sure all of our research is relevant. We actually have a question in the Q&A related to that, which I'll move on to. How do you, in your role, engage with industry to ensure research is kept relevant? I guess to kind of add to that, do you have main partners that you work with that you get feedback on before deciding on research topics?
Yeah, so it's a mix of different things. So, for example, when you apply for a big research project, you usually would want industry to be part of this, because researchers know that we're in danger sometimes to get lost in all the different rabbit holes, right? We don't want to research for years and years and then be told, oh yeah, we don't need this at all. So it's, I think in general in research there is the awareness that you need to involve industry on some level anyway, and then a lot of research projects want you to generate demonstrators as well to showcase, okay, we've done all this research, but we're thinking of this application, and we show already, okay, this is possible, and these question marks are still left open. Yeah, so it's a lot about the conversation. That conversation needs to happen between industry and research.
Yeah, absolutely. So important. Well, that concludes this session. Thank you so much, Fiona. That was really a really valuable session. We've actually got you on our next panel as well, but I'll give you a few minutes to grab a drink and come back. So thank you, everyone, and I'll see you back in a few minutes' time.